Good morning to all of you. In previous sessions, we were discussing about various properties of Fourier transform. We have seen linearity, time shifting, time reversal, convolution theorem, correlation theorem, and Wiener-Keitzel theorem. So today we'll be discussing frequency shifting and modulation theorem. So first we'll discuss the frequency shifting property. So as per the Fourier transform of x of n can be represented as x of omega, right? And the formula for it is summation n is equals to minus infinity to infinity x of n into e to the power minus j omega n. Okay, so as per the frequency shifting property, if x of n, that is discrete time signal x of n, as the Fourier transform x of omega, then e to the power j omega 0 n into x of n will have the Fourier transform x of omega minus omega 0. So the multiplication of the sequence x of n by e to the power j omega 0 n is equivalent to a frequency translation or Fourier transform of the spectrum x of omega by omega 0. Okay. So this x of omega has been transformed, or its frequency has been modified as omega minus omega 0. So it has been modified by omega 0. So you can prove this property, right? As here we are interested in identifying the Fourier transform of e to the power j omega 0 n into x of n, right? So as per the formula for Fourier transform, it will be n is equals to minus infinity to infinity in place of x of n, right? Here value is e to the power j omega 0 n into x of n, right? Into, so this has been written in place of x of n, right? Into e to the power minus j omega n will be there, right? I'll just rewrite this equation here. So what we have, n is equals to minus infinity to infinity. I'll just adjust these terms. So I'll write x of n initially. So x of n into e to the power, so that j e to the power j omega 0 n, right? Into e to the power minus j omega n. So I can again rewrite it as n is equals to minus infinity to infinity x of n into e to the power. So if I'm taking e to the power j minus j into n common, so in bracket I will have omega minus omega 0 into n, right? So if you compare this particular equation with the formula of Fourier transform, right? So in place of e to the power j omega n, this has been written or denoted as x of omega. This complete equation has been denoted as x of omega. So in place of omega in this equation, here it is omega minus omega 0. So as it has been indicated as x of omega, this can be denoted as x of omega minus omega 0. Okay, so that is the proof of this theorem. Right, again you can apply this theorem to identify the Fourier transform of the discrete time signal, which is multiplied with e to the power j omega 0 n, right? So this is nothing but the frequency shifting property. The second property that we will be discussing today is the modulation theorem. Okay, the modulation theorem. So again, as per the modulation theorem, if there is discrete time signal x of n with Fourier transform x of omega, then the modulated version of x of n, so x of n multiplied by cos omega 0 n will have the Fourier transform 1 by 2 into x of omega plus omega 0 plus x of omega minus omega 0. Okay, so this is as per the modulation theorem, right? So again, we can prove this property. So here we are interested in identifying the Fourier transform of x of n into cos omega 0 n. Okay. So as per Euler's identity, we can represent this cos omega 0 n as 1 by 2 e to the power j omega 0 n plus e to the power minus j omega 0 n, right? So basically we will try to identify the Fourier transform of x of n into this cos omega 0 n can be replaced with 1 by 2 e to the power j omega 0 n plus e to the power minus j omega 0 n. Okay, so we will be interested in identifying the Fourier transform of this complete equation. So as per the again formula for Fourier transform, so it will be n is equals to minus infinity to infinity. In place of x of n, this equation will be there, right? So here you can simply write it down as was 1 by 2 is the common, so you can take outside summation, or I will just write down here for now, and then inside bracket I will multiply these terms with e to the power x of n multiplied by e to the power j omega 0 n plus x of n into e to the power minus j omega 0 n, and multiplied with, as per the Fourier transform formula, this is nothing but your x of n multiplied with e to the power minus j omega n. Okay, so x of n multiplied by e to the power minus j omega n is nothing but the Fourier transform formula, right? So again I will just rewrite this equation with certain modifications. So 1 by 2 I taken outside summation n is equals to minus infinity to infinity is there, right? So here I'll just separate these summation terms, right? So I can write it down at summation n is equals to minus infinity to infinity x of n into, is that here we have e to the power j omega 0 n, e to the power j omega 0 n multiplied by e to the power minus j omega n, e to the power minus j omega n, plus again summation n is equals to minus infinity to infinity, again x of n is there, right? X of n multiplied by minus j omega 0 n, e to the power minus j omega 0 n multiplied by e to the power minus j omega n, right? So again I can rewrite as 1 by 2 summation n is equals to minus infinity to infinity with x of n multiplied by, if I am taking e to the power minus j common from here, so it will be omega minus omega 0 n, right? Plus summation n is equals to minus infinity to infinity x of n into, again it will be, I'm taking minus j common, so it will be omega plus omega 0 and will be there, right? So you can prove like this, or you can directly apply the frequency shifting property that we have seen in the previous slide. If I am identifying the Fourier transform of x of n multiplied by e to the power j omega 0 n, so it will be written as per this frequency shifting property, or you can again here compare these formulas with the formula of Fourier transform. So in Fourier transform formula, here only omega is there, right? So in place of omega, as omega minus omega 0 is there, so we can simply represent it as, instead of x of omega, we can represent it as x of omega minus omega 0, right? Plus similarly here, in place of omega, the value is omega plus omega 0, right? If you compare this formula with the formula for frequency, this Fourier transform, right? So again, in place of x of omega, I can write it down as x of omega plus omega 0. Okay, so this is nothing but the required proof of the this modulation theorem, right? So again, you can identify the Fourier transform of the discrete time signal, which is multiplied by the cos functions, right, by using this modulation theorem. Okay, so these are the two equations or two properties, that is frequency shifting property, and second one is the modulation theorem property, right? So uh, in next session we'll be discussing another property that is differentiation in the frequency domain. Okay. So thank you for joining this session.